Ashok, you have to.
Yeah, I can do that. Resume recording.
Okay.
This meeting is being recorded.
So you can just pause it now and then you can resume it when we start or something.
Yeah.
Yeah, I was just seeing the button of where to stop recording. Yeah, okay, now I got.
I can just recording in progress. Hello, my name is Kit Roscoe. I'm the communications guy from the African Health Research Organization, and we are a non-profit institute which promotes global health through research, education, publications, and events such as this. This is actually our first webinar, so excited to see how it goes. We also do community interventions. Now, we are the publishing arm of the organization, and we publish books, journals, and we actually won the Scotland Prestige Award for Specialist Publishing Company in 2021 and 2022. So who knows, maybe we might win it next year as well, fingers crossed. AHRO also runs the AHRO University, which is in the making. This is going to be sort of educational institute, which is postgraduate, and it's going to be 80% online and 20% on site here in the sunny, very rainy Glasgow. This is, as I said, our first webinar, and we are going to have quite a few actually, with some boffins each month throughout the year. So I will put some links to the social media in the chat box, and you can keep up to date, easy peasy. Now we'll set some ground rules to the webinar. Keep muted and keep your camera off. Basically, the internet might be quite slow, and if there's lots of video, it can weaken the bandwidth. Lots of technological stuff that I don't quite understand, but just don't turn your video on. And because of the length of the webinar, we might not have a chance for Q&A at the end. So if you have any questions, put them in the chat box along with your email address, and we can answer them over the next coming week. Also, if you stay for the whole thing, which I'm sure you will, because this will be riveting, certificates of attendance will be emailed to everyone. And along that will be a small survey, just to see where we went right, where we went wrong, because it's interesting. We need your feedback and input, so we can keep doing these and making them better. And also, if you want to watch it again, it's going to be on YouTube. So Professor Ashok Rattan is the man of the hour today. He will be presenting our inaugural webinar. He's the chairman of the medical committee and quality at Redcliffe Labs, and is a highly respected academic. So a bit of a medical celebrity here today. Very lucky to have him. A medical microbiologist, and has held very important positions in academic and industrial institutions, diagnostic labs, I don't know these terms, but tertiary care hospitals and public health institutions. He's temporary advisor and lab director to the WHO, and a recipient of the APJ Abdul Kalam Award for lifetime contributions to medical science. So before we jump to Ashok, I will hand you over to the big cheese here, Professor Yarrow, Abubakar Yarrow. I think he wants to say a couple of words. You're muted.
Yeah, so thank you very much, Kate. And specifically, I welcome you all, and specifically welcoming Professor Ashok, who has been a good, should I say, a good friend, a good teacher, and a good brother to me. So today, Prof. Ashok is going to speak on tackling the
invisible pandemic.
Yeah, the invisible pandemic. Yeah.
Before it becomes invisible.
Yeah, so as we all know, antimicrobial resistance has become quite a huge global public health burden. And, so many names have been, associated with antimicrobial resistance. I normally call it the silent pandemic. So there have been so many technology or strategies that have been developed for us to tackle antimicrobial resistance. And one of the strategy has been the stewardship program, which a lot of paper has shown that it plays a part in the reduction of antimicrobial resistance. So as the days goes by, new improvement have been added to antimicrobial stewardship. So issue like this should be discussed by an expert, and I'm so much honored to have Professor Ashok here to come and speak to us on the topic about antimicrobial stewardship. So over to you, Professor Ashok.
Thank you. I will load my slides now. Can you see my slides?
Not yet, Professor.
Now?
Kit, is Professor the host now?
Let's just see.
Yeah, no, you need to make me host.
No, yeah, Ashok is the host.
Oh. You are the host, Professor Rattan.
Can you see the slides?
It's not showing.
Okay, screen share, tackling the invisible pandemic. Now?
Yeah, now it's good. Yeah.
Yeah, no, see, thank you.
Okay, so good morning, good afternoon, good evening, wherever you are. And let's start seeing how we can tackle the invisible pandemic before it becomes the invincible pandemic. We all know that on 31st December 2019, WHO informed regarding an outbreak of pneumonia caused by a novel coronavirus in Wuhan. Within 10 days, one full sequence of this RNA virus was available. By the next day, 5 more were available, and it was soon identified as SARS coronavirus. And since it differed from the earlier one, this was called SARS coronavirus 2. The next 2 years were consumed by a pandemic, which was declared as a pandemic on 11th March 2020. It caused disease in 640 million cases, taking about 6.6 million deaths. Diagnosis played a very important role in control of disease, even in identifying that the disease exists. In India, the Indian Council of Medical Research ramped up its labs to detect COVID-19. In January 2020, when we first heard about the virus, there was only one laboratory, the National Institute of Virology, which could identify the virus. By September 2020, there were 2,234 labs which were accredited for being able to do RT-PCR. The industry also responded by making copious numbers of tests available, be it molecular test, and now even a layman knows what is RT-PCR, or the serology, or antigen testing. At the same time, vaccines were developed at pandemic speed, and then the take-up of vaccine was much higher than the population of the world. Even now, though, as you notice here, 91, 94, 14, 384, 382 tests have been done cumulatively in India. Even on one day, 36,000 tests are being done, and there are 3,393 labs which can now do RT-PCR. So COVID-19, a very visible pandemic, took a great toll in life and economy. But now that we have pushed the pandemic in the background, we must address another pandemic, which is not so visible. And that's why either it is called the silent pandemic or the invisible pandemic. But anybody who knows anything about it is scared that soon it will become the invincible pandemic. We all know that antibiotics are rampantly used in lesser developed countries. They are used in tons in India, and it's been projected that between 2001 and 2010, the consumption of antibiotics grew by 62%. And it is anticipated that it will grow even further between now and 2030. In a recent paper in Lancet, it was mentioned that cephalosporins and penicillins constitute the maximum daily defined dose that is being administered in India. The consumption of systemic antibiotics in India have been examined, and what is concerning is that only 27% of what is defined as excess antibiotics are used, while the reserved antibiotics, though used less, but it's been noticed that antibiotics, which constitute 72% of the daily defined use, are normally either unapproved products or combination which are discouraged by WHO, which constitute 48% of all consumption. In a previous paper, data from Europe had indicated that the more the consumption of antibiotics, the more would be the resistance. When you extrapolate India's consumption, which is about 10.4 DDDs per 1,000 patients, you notice that it is like that of Spain or Italy. The reason why antibiotics select for resistance is very clear to understand. And that's why WHO has classified all drugs into excess drugs, which should be made accessible to everybody, watch drugs, which should be used with caution, and reserved drugs, which should be used only when indication is very clear. What would happen is that mutations will occur. Mutation in the target gene of the bacteria occurs during the course of multiplication. Once that group has become resistant, one bacteria in a million have become resistant, then you add antibiotics to it, and what would happen is that there is selection of the resistant mutants. Soon, the sensitive bacteria are all wiped out and are replaced by resistant bacteria. So the current crisis of MDR infections has two parts. One is an act of God, that is nature, which means that whenever the bacteria multiplies, there is mutation in the target gene, and this mutation in the target gene will confer the ability of bacteria to be able to survive against the antibiotic. Second one is that this mutation would spread from commensal bacteria or bacteria in the environment to bacterial pathogens. Once these pathogens have acquired the gene, then act of mankind takes over. When we give antibiotics, selection of resistant mutants will occur, and because of lack of sincere efforts at hospital infection control, there is then spread from one person to another person. So there is selection of, so these are the 4 steps. Part of it is act of God, which you and I cannot do anything about. But the second part is act of mankind, where we should actually focus our attention for containment. It's also been noticed that antibiotics are not something that are used only by human. In fact, 70% of all antibiotics produced are used for animal husbandry. This is not for sick animals, but as growth promoters. Animal use is only 9% of the total antibiotics are used for human therapeutics and 6% for non-therapeutic or prophylactic purposes. So the total consumption is only 15% of the total antibiotics used in the world. So to restrict our efforts only at human antibiotic use will not subserve the purpose. Even if the antibiotic used in human varies from 19 to 15%, at least 30% of that antibiotic use is unnecessary. And that could be because it is given for too long, or for non-infectious purposes, or for treatment of colonization of or contaminants. We need to also understand that 4 things happen simultaneously whenever antibiotics are used. One is clinical cure, and that is what we want. But the 3 unintentional activities that occur is inhibition of non-pathogenic bacteria, selection of resistant mutants, and if the antibiotic recognize any target on human cells, then there is side effects or toxicity. It's been suggested, again, I keep thinking that these are all guesstimates, but it's been suggested that in 2019, 495 million people died with drug-resistant bacterial infection. Of these, 1.27 million deaths were directly caused by antibiotic-resistant bacteria. It's been also guesstimated that if we do not do many things that we are going to suggest, then by 2050, antibiotic-resistant bacteria would be the largest contributor of death in the world. In 10 million cases, 10 million deaths might occur by 2050. We all know that bacterial infections have frequently caused pandemics in the past. Most of you would be aware of the Great Plague, which occurred in Europe in 1660. Then, about 200 years later, there was this Crimean War in which Florence Nightingale, who spent time with the patients, realized and noted that more deaths were caused by infection than from wounds in the battle. So I would suggest that antibacterial development and discovery and development was one of the greatest achievements of the 20th century. The heroic surgery, including heart transplant, kidney transplant, liver transplants, and now even lung transplants, have been made possible because of the umbrella of protection provided by the antibiotics. Of course, technical competence of surgeons have also improved, but it is because of the protection provided by antibiotics that it's been possible to. When you compare the deaths which occurred before antibiotics were discovered and used, or after now that the antibiotics are available, you would find that there's a drastic difference between what used to happen in community-acquired pneumonia or hospital-acquired pneumonia or heart infection, brain infection, and skin infection. The change was between 10% to 75%. Just as a comparator, the aspirin that we take to prevent clotting after a stent has been placed in us makes a difference in only 3%. In the past, industry was quick in adding new antibiotics. Every 2 years, a new class of antibiotics would be added between 1940 and 1962. And this era could be classified as the golden era of antibiotics. Thereafter, there was a plethora of Me Too drugs where they would say this is first generation, second generation, third generation, etc. And it took a lot of efforts and ingenuity for medicinal chemists to then synthesize new molecules. And oxazolidinone, which was initially tried as an antihypertensive drug, was the one found to have activity against MRSAs and other gram-positive bacteria. Subsequently, in the recent past, boronic beta-lactam inhibitors have been added, and many of the cephalosporins have been coupled along with boronic beta-lactams. But the fear of after antibiotic era is real. One of the problems why this is occurring is that we have had so-called wise persons who would be giving various advice. I think the plug was pulled when the futuristic looking towards the year 2000 suggested that the time has come for bacterial infections and viral infections to be all wiped out. Bacteria who do not attend conferences and do not listen to these experts merely kept on acquiring more and more resistance. And this is an old slide I've been using for many years, but you'll notice that all significant gram-positive bacteria have gained in resistance since the last decade or so. But because of the advice of so-called experts, many large pharmaceutical companies have stopped investing in discovery of new antibiotics. And as a consequence, regulatory approval of new antibiotics is coming down, while that of cancer drugs and antiviral drugs are increasing in number. So we have a basic problem. While resistance in important pathogens is increasing day by day, investment and discovery and introduction of new and novel antibiotics have decreased. When you look at the targets, this was the time we discovered antibiotics when we knew very little about the physiology of the cell, of how the antibiotics will work. And still, at least 7 different types of targets were identified. Now that we have the whole genome sequencing of hundreds of bacteria, and we have combinatorial chemistry and high throughput screening, the number of new tests, new targets identified are listed here. It's a blank sheet because there have been no new drug identified in the recent past. So it was of great interest that just a couple of weeks back, a conjugated oligoelectrolyte, which had activity against gram-negative as well as gram-positive bacteria and was not toxic to human cells, was identified. This mimics part of the lipopolysaccharide, which forms part of all gram-negative bacteria. And it appears that this scaffold might be used for soon making an antibiotic, which will work against all antibiotic-resistant bacteria. But one of the discovery of antibiotics normally have come from nature. There was a priest who took some soil from the rainwater forest of Borneo and handed it over to Edmund Cornfield in Elilili. In 1959, a extract known as 0586 was identified from the bacteria, which was the higher bacteria, which was isolated from the soil. This was active against gram-positive bacteria only, and there was no development of resistance after various in vitro passages. This was named as vancomycin, thinking that we have now vanquished the antibiotic resistance, and FDA gave fast-track approval. It was also called Mississippi mud because of the impurities which were present. Subsequently, by using HPLC, the recently available vancomycin has been clarified and is no longer as Mississippi mud, but it's effective against MRSAs, but with the appearance of visa, the fear was that now vancomycin-resistant Staph aureus would also make its appearance. So because MRSA had already become visa and VRSA was emerging, so teicoplanin was discovered, followed by linezolid, daptomycin, and ceftaroline, and following that, FDA has approved delfaflexin and many others. So it would appear that as far as gram-positive bacteria are concerned, because vancomycin and teicoplanin is available, linezolid is available, daptomycin is also available, and tetracycline and ceftaroline is also available. So against gram-positive bacteria, we have the problem nailed down. But for gram-negative bacteria, we had only tetracycline and colistin. and one wrong turn could leave us severely exposed. A paper was published about bad bugs and no drugs and no escape. But you would notice that Staph aureus and Enterococcus faecium has been covered, but gram-negative bacteria continue to pose a problem, to which you can add gram-positive bacilli as Clostridia difficile. A number of new drugs as combinations of boronate beta-lactamase inhibitors have been made available, and they cover various parts. But it should be clear that extinction of MDR bacteria is not an achievable goal. Bacteria have inhabited the earth longer than humans and in far greater number. Humans have the capability of causing extinction of other species, mostly unintentional. Dodo has been made extinct. Tiger maybe is going to become extinct, but bacteria will not be extinct. So therefore, what we need is antimicrobial stewardship. And antimicrobial stewardship should integrate data from the clinical data, quality and quality of care data, and microbiology data, and put all this together so that there is improvement in day-to-day cure and QI projects are initiated. It needs for antibiotic stewardship program to succeed, it needs the patient to be kept at the center of all the activities and to involve the nurses. The ID, microbiology, and pharmacology persons are always involved in antibiotic stewardship program. You would find that medical superintendent, nursing superintendent, and the infection control committee are also interested. But what is lacking normally is the involvement of physicians who prescribe antibiotics and the surgeons who stand to gain the maximum if we can prevent resistant bacteria for ruining the excellent work that they do in the operation theater. The competencies required from microbiology have been defined as that from pharmacologists as well as from the ID physicians. It is disheartening to note that ID physicians are present in developed countries, but in developing countries where every second person has an infection, ID competencies are normally either shared by everybody or non-existent. Many reasons for this failure of antimicrobial stewardship have been suggested. My take on this is that there is underutilization of pharmacists and nurses in antibiotic stewardship program. There is lack of leadership, expertise, and human resources in antibiotic stewardship program. There is limited involvement of surgeons and physicians as active members of antibiotic stewardship team. And there's lack of appreciation of its importance by health administrators. So what is antibiotic stewardship? Antibiotic stewardship is skillful management of limited resources that we have so that the right antibiotic is given to the right patient at the right dose, at the right time, by the right route, for the right duration. This is essential for patient safety and for delivery of high quality care. There are 4 moments of antibiotic decision making. The first one is, does my patient have an infection that requires antibiotics? Have I ordered appropriate cultures before starting antibiotics? after a day or more has passed, can I stop antibiotics? Can I narrow down and de-escalate from IV to oral? And what duration of antibiotic therapy is needed for my patient's diagnosis? We had written an antibiotic use bundle, which had day 0 and day 3. Before starting antibiotics, we should document, the clinician should document, and this is the initiation bundle. What is the evidence that there is a bacterial infection? Collect and submit appropriate cultures, remove any foreign body or do IND if there's any collection of pus, and select the plan and plan the antibiotic used based on local antibiogram. Which antibiotic, what dose, which route, and how frequently. And not change the antibiotic they've chosen for at least 3 days. Now, every microbiologist I meet, they say that they produce results which help the clinician select what antibiotic to use. But their results take 72 hours to be available, so that when a person comes to the ER and he has an obvious infection, the results would take 72 hours before they're made available. So if the microbiologist want to influence the empiric use of antibiotics, they must collect and circulate cumulative antibiogram, which indicate what are the resistant pattern in the last 1 year in the area that they're working. It is clear that antibiotics should be used quickly and used adequately, because every hour of delay decreases the chance of survival by 6 to 9%. But before you can help, you must make sure that your lab is up to date. If it is only smear microscopy and manual cultures that you're going to offer, then if Robert Koch, who discovered tuberculosis in 1882, if he visits your lab, he would have a sense of déjà vu. Even in tuberculosis, we say that in 1882, when people used to use horse carts, they discovered tuberculosis by using smear microscopy. In 2023, where Mercedes are running on every road, you would find that using the same smear microscopy would defeat the purpose. For smear microscopy, at least 10,000 bacteria must be present in the sample. Otherwise, the report will be negative. While using a new system known as BD-Max, 1 bacteria can be identified in the sample, and that will report also on INH and rifampicin susceptibility, so that by the end of the day, the person can be put on the right antibiotic. WHO has recommended that the initial test should not be smear microscopy, but a molecular test. And they have approved 5 different categories of molecular tests that can be tried. One of the commonest methods for finding out infection and sepsis has a mortality of 30% is doing blood culture. Instead of doing manual blood culture, we must do automated blood cultures. And because the bacterial load per ml in a child or a neonate is higher, only 1 bottle with 1 to 3 ml of blood is adequate to identify the causing bacteria in children. On the other hand, for adults, we must have at least 2 sets of 2 bottles, each containing 10 ml. So for an adult to pick up the right bacteria, you have to use at least 4 bottles. Each of these bottle has an indicator at the bottom, and there's a semi-permeable layer which separates the medium in which the bacteria will grow and produce carbon dioxide. The carbon dioxide will then will come across the semi-permeable membrane and would be then detected. All these bottles after inoculation are placed in individual chambers which are rotating, and at the bottom there's a lead which every 10 minutes will shoot out light, LED light, to see whether there is a change in color. And the moment the color changes and this is persistent, then the bottle will flag that as positive. This works 24/7. As a consequence, most of the bacterial infections can be identified within 5 days of blood culture. As I said, at least 2 sets are required, but work has also shown that if you use 3 sets, then 96% of all pathogens would be identified. Once a bacterial bottle has flagged as positive, then a smear should be made, sharing the information as a critical call out to the physician would help them modify the antibiotic that they are using. In the recent past, Multi-Toff has also been applied to vaporize the bacterial components and then move the bacterial components through a vacuum where they will give rise to a trace, and looking at the trace and comparing the trace with the library, you can, in 2 to 3 minutes, you can identify what the bacteria is. At this moment, only bacterial identification is possible, while using Multi-Toff alone, you cannot know about the sensitivity. That's why it's been suggested that you do a rapid sensitivity test from a positive blood culture bottle. But recently, it's been suggested that you can use a reveal rapid AST, where you place the blood culture bottle, place the material from blood culture bottle in a 96 well plate, which have various concentration of different antibiotics, and then place a cover over it, which has sensors, volatile metabolites, which will be released during the growth of the bacteria, will act with the sensor and will give different color. And looking at the color, you can then give MIC in 2 to 3 hours. Of course, MIC is a static data. That to convert static report into a dynamic report, you need to understand the level of Cmax. That means the height by which the antibiotic delivered will be given, what is the area under the curve, and what is the time over MIC. But MIC plays a fundamental and important calculation in all these PK/PD parameters. At the same time, you've always wondered, if we were supposed to save lives in sepsis, then we should be able to detect bacteria or the pathogen without having to culture. T2MR biosystems, which is a microbial resonance system, has made that possible, that in 3 to 5 hours time, without having to culture, you can identify whether Candida is present or sepsis caused by Staph aureus, Klebsiella pneumoniae, Pseudomonas aeruginosa, or E. coli present, and whether the bacteria contains MEC A or C genes, which is against colistin, WAN A or B genes, or CTX genes. So using T2 MR system, it is possible to identify whether a pathogen is present, and then to do sensitivity test to identify, and then combine it with PCR and MALDI-TOF. It could be faster. Of course, so using the recent methods, it is possible to rapidly diagnose the test and give antibiotics. In the recent past, curious test has been also developed, which is PCR.
Almost 2.8 million hospital admissions in 2021 in the U.S. were due to infections,
which consist of sample collection, DNA extraction, pre-sequencing, sequencing using millipore, using Oxford millipore, and then data analysis and report generation all in one day.
And what we showed is that the analytical sensitivity of the Karius test was 95%, with a specificity of greater than 99.9%. The clinical validation were adult patients that had suspected sepsis presenting to emergency room, and the Karius test was compared to blood culture as well as biology results. And what we found is that the Karius test was 2.7 times more likely to identify that causal pathogen than a blood culture. When it was compared to all microbiology tests, it was 1.3 times more likely to pick up a causal pathogen.
So there's also been thought, one is, so I've taken you from a smear microscopy to the Karius test, which is a multiplex whole genome sequencing based identification of thousands of bacteria or pathogens which may be present causing sepsis, especially in immunocompromised patients or those who have had organ transplant. But one fundamental question that WHO has been asking is that antibiotics should be given when there is evidence of bacterial infection, and it should not be given, it should not be prescribed or given when there is viral infection. So the question is that if you have, is there a simple biomarker available that can help you differentiate between bacterial infection and viral infection? Procalcitonin is such a system where procalcitonin is a 116 amino acid precursor of calcitonin, which is used by thyroid cells, and it is then converted into calcitonin. But only thyroid cells have the ability to convert procalcitonin into calcitonin, which then comes up, and it has effect on calcium metabolism. But procalcitonin is normally produced only by thyroid cells, but whenever there is an infection, a bacterial infection, especially because of lipopolysaccharide, it will lead to production of nearly all cells will start producing procalcitonin. And since they don't have the ability to convert procalcitonin into calcitonin, the level of procalcitonin in the blood will increase. On the other hand, if there's a viral infection, that this viral infection.
Hi, sorry, Dr. Singh.
Neha Singh, please mute yourself.
Could you mute your account, please, Dr. Singh? Or if whoever the host is, just say mute Dr. Singh. Rattan, if you could mute.
Dr. Neha Singh, please mute yourself.
I think you can mute him. You can mute him yourself.
So if there's a viral infection, the viral infection the viral infection will produce interferon gamma, and this interferon gamma will decrease the production of procalcitonin.
Sorry, this is really distracting. Professor Rattan, you can manually mute Dr. Singh. No, thank you.
So a viral infection will produce interferon gamma, and interferon gamma will decrease the production of procalcitonin. Therefore, if there's bacterial infection, then the level of procalcitonin will rise. The level of procalcitonin will rise in 3 to 6 hours, and
I want to go. Wait.
The level of procalcitonin will rise and it will remain high, and it has a half-life of 24 hours. So if you do serial estimation of procalcitonin, if the levels have risen and you have given appropriate antibiotics, the level will start falling. If, on the other hand, it continues to be high, that would mean that your antibiotics have not had any effect in case of the bacteria that is there, and so the bacteria is resistant and you must change. Numerous guidelines have been made, and consensus is that if the procalcitonin levels are in nanograms per ml, and if it is less than 0.25, then then antibiotics should not be given, because it's not a bacterial infection. While if it is more than 1 and you feel that there's infection, then you must give these antibiotics. It has been noticed that sometimes procalcitonin levels can be higher as a consequence of trauma or surgery, and so you should use this prudently. Initially, procalcitonin used to be available only as a centralized system, and it would take time, but now many point-of-care testing is available, and they are quantitative, and I would strongly recommend that you use it. There was a study in America where they had antibiotic use depending upon procalcitonin, and they report that they saved $6 million in 1 year time using this system. When I talked to my colleagues, they said they don't use PCT because they feel it is costly and it's a sent out test. That has been taken care. Now point of care testing is available. And I think in developing countries, if they do more cost-effective analysis, you might find that the patient or the society would save time and energy by not using antibiotics unless procalcitonin is high. All right, so then now that a number of tests are available, the aim is to use the right test for the right patient for the right time and have the right interpretation, and then use the right antimicrobial. So diagnostic test could be used for rapid diagnosis, and they would be able, once you can rapidly identify bacterial infections, then antibiotic misuse will decrease. It can also detect the presence of resistant bacteria on admission, so that by screening, you are forewarned that this patient is carrying resistant bacteria. This diagnostic test could also help in resistant trends, and surveillance is very important for making decisions and writing protocols. Turning plans into action has been one of the concerns of WHO, and they have suggested 6 different strategies for success. And they suggest that there should be a central coordinating committee. There would be many of the activities are already undergoing, which help in decreasing of antimicrobial resistance, and that should be taken on board. And we must be able to also identify and engage persons to explain who's to be engaged and for what purpose and how it should be done. However, it's been noticed that though more than 200 antimicrobial stewardship programs have been tried, the overall effect of this has not been adequate. It's been suggested by Professor Eccles that it is because of Islagate principles. Islagate principles means that it seems like a good idea at that time. And normally the missing link is that antibiotic stewardship program do not work because they do not address the behavior change that we are seeking. The key principle of successful change is choice of intervention should be informed by the determinant, the barrier or facilitator that influence current behavior, and behavior change psychology offers theories, frameworks, methods, and understanding what drives behavior and how to use this to be more effectively. We must be careful that there's no magic bullet or universal truth. But a paper published in Journal of Antimicrobial Chemotherapy indicated that if we want to change what we must first be clear, what behavior are we trying to change? Why is the current behavior as it is? What would it take to bring about the change? And then match choice of intervention strategy to behavioral diagnostics. The BOMB principle give a framework for identification. This talks about capability, motivation, and opportunity. The capability, motivation, and opportunity drives our behavior. So we must know what is the capability that we are able to change, what is the motivation of change that we have, and what are the opportunities in the environment that will change our behavior. For that, a behavior wheel has been created, which consists of capability, motivation, and opportunity. Then this is covered by intervention functions, what interventions we can cause, and then what policies need to change so that the right activities should take part. As a consequence, totality would help us change the behavior. So we should not try to offer quick fixes to most of these changes. First is to understand the behavior, define the problem, select target behavior, specify the target behavior, identify what needs to change. Then is identify intervention options. And finally, identify the content and implement strategies. Here, as you notice, that we've talked about the theoretical domain framework, that's COMB model, behavior change wheel, and behavior change techniques and technologies. So what first is to identify what is it that we want to change, and then to see in the behavior mode what are the capabilities, what is the motivation, and what is the opportunity. And as far as ARM is concerned, is variable. There is variable understanding of ARM, what antibiotics can and cannot do, variable use of and awareness of guidelines and frame and prescription habits, fear of missing something or letting patients go without ARM seems without antibiotics is one of the fear in the doctors, especially in ICU. ARM is seen as a distant threat by some of the persons, and so on and so forth. And diagnostic tests must be available. But besides this, we can also use vaccines. As you notice here, that Haemophilus influenza B was an important cause of death in under 5 children. Once they had vaccine, again, which was a polysaccharide vaccine, the polysaccharide vaccine did not work in children below 18 years of age, 18 months of age. So once they gave to persons, they did not make too much of a difference. Then the conjugate vaccine was made available. But again, it was limited to children above 18 months. Finally, when a first Haemophilus influenzae vaccine, which became available for infants over 2 months of age, when that was introduced, you were able to nearly wipe out Haemophilus influenzae B infection in many of the places where it was used. Similarly, it can be done with pneumococcus, and of course, I think it should be done with Salmonella typhi, because the VI vaccine available is excellent and gives protection. And all of us who live in tropical countries are susceptible to typhoid. But as I said, we know that antibiotics are not use is not restricted only to humans. It's used in agriculture and it's used in animals, and only 30% of use if it's going to increase. If in human use is going to increase by 30%, 70% is being used by the animals, and it'll increase in tons. So what is required is we think of one world and one health. One health means that simultaneously we study the effect not only on human health, but also animal health and in environment. And there are various strategies suggested to work for one health for ARM. And then when we are thinking about one environment, animal health and human health, one health, it will also mean one world, because antibiotic stewardship program and antibiotic resistance do not understand any visa requirements and limitations of persons. And we know that there are different categories of drugs which are critical for human beings and for animals. But we must try to do our best so that we decrease the inappropriate use of vital drugs like colistin and penicillins for animal husbandry and provide better environment. So there's a need to do individual health, one health, and global health. So in conclusion, for tackling the invisible pandemic, we need to work on national policy, on global funds for infrastructure development, regional and international collaborations, developing new antibiotics, infection prevention, ban on OTC sales of antibiotics, ban on growth promoters in animals, anti-stewardship, public-private partnership, surveillance and monitoring, awareness in public, and vaccination. At the same time, it must be clear that every action, every person, every action, every day, we have the power to stop infection together. And we must be aware that antibiotic stewardship can leverage the butterfly effect of hand hygiene. Butterfly effect means small actions which can have large consequences, and hand hygiene is one of the most important element in infection control. So what is it that each one of us can do? There are 10 ways in which we can make a difference. One is to think globally, act locally, make it personal, make the invisible visible, think outside the hospital walls, refrain from the safe side and just in case use of antibiotic, meet the public where they are, leverage awareness of COVID-19, use evidence-based messaging, and keep conversation going all throughout the year rather than only during the week that we call as Infection Control Week. I thank you for your attention, and I hope that I would have stimulated you to now act some more on this. In the next meeting on 31st, we will talk about clinical standards for management of drug-susceptible pulmonary tuberculosis. The timing will be the same, that is 12 noon in UK, but of course, since they will be using the new timing, it will be 1 hour difference for Indians and other colleagues. I thank you for your attention.
Thank you. That was fantastic. Professor Abubakar, would you like to do the closing statement?
Yeah, thank you very much, Prof. Ashok. You know, I always say Professor Ashok normally present a difficult subject in a very simple way for everybody to understand. And today he didn't disappoint. I think from the beginning, he has given us a brief statistics or epidemiological statistics of AMR. And, you know, he started with mentioning the name invisible pandemic. And I also normally call it the silent pandemic. In fact, today I've been able to add one thing to what I also know, that antimicrobial resistance has two causes, the act of God and act of human being. So this means that at the end of the day, we might not be able to, you know, end AMR. But as Professor Ashok said, the aim now will be containment. So he has given us a projection of what might happen in 2030, where if we are not careful, about 10 million people will die to AMR. So it means all of us have to play a part towards containing AMR. So when it came to antimicrobial stewardship, he gave us some figures. He showed us how to diagnose AMR, and at the end of the day, the possible, you know, novel solution on how to control AMR. So at the end of it, he made a very strong recommendation. Let us all join the train that will help, you know, in the containment of AMR. So based on that, I think AHRO is a dynamic organization. We are always trying to fill in gaps, knowledge gaps. So as he was speaking and towards the end, I also came out with some sort of initiative. Let us form the antimicrobial resistant group within AHRO. That will be, you know, carrying evidence-based research to help, you know, fill in some knowledge gap in antimicrobial resistance. So I think there is an email, info@ahro.org. Any of the participants who want to join that group can send in, you know, their interest. Then we take it from there. So Professor Ashok, thank you. We look forward to the next webinar. I think there are a lot of webinars. So as we go, as time we're gonna keep on going, we'll be notifying participants of next webinars here and there. So Professor Ashok, thank you very much. Anybody with any question can either, I think now it's late, so you can send it to that email that has been stated in the chat box. I think that's what I have, yeah.
Excellent. Well, if that's us, then I'm sure we can all go our separate ways. But thank you again. And I hope to see everyone here on the 31st for will be another riveting hour. Thank you and goodbye.
Thank you. Thank you.
Thank you, sir.